Here's the spiel that will apply to all of them. It is very important to get a sense of what's linear and what's not linear. And right now I'm using the word linear in a very broad, somewhat vague sense. But mathematicians, engineers, and all technical sciences have a great feel for what's linear or not. And it's one of the first things when first faced with a problem that we judge. Is this problem linear or not? We almost can't help that judgment. Just like when you meet a person in the street that you don't know, you can't stop your brain from processing the gender of the person, the age of the person, the height of the person, all of that registers. You can't tell yourself not to recognize those aspects of a person. So for a mathematical problem, perhaps the most important aspect that you always try to ascertain first is whether or not it's linear. And in linear algebra, the term linear takes on a very precise sense. And that sense is the set that's being described a linear subspace? That's really all it is. Is it a linear subspace? And if it is, we'll call the property that describes it linear. And if it's not, we'll call the property that describes it nonlinear. And to break it down a little bit, whether something or not is a linear space means one thing only, two things only. Whether or not it's closed under addition and multiplication by a number. In other words, and it truly is different words to say the same thing, whether the property survives addition and multiplication by a number. Put them together, we would call that nonlinear. For a function, it means if we take two functions that belong to this set, in other words, satisfy this property, we'll ask, does their sum still satisfy the property? And does a number times one of these functions still satisfy that property? And if the answer is yes, the property is linear, the set represents a linear space, and we're happy. We can do linear algebra on it. If it's not, then we essentially cannot do linear algebra on it, and all of the ideas that will be introduced in the future will not apply. Or maybe will apply with some adjustments. Okay, so let's take a look at part A. Translating what you're reading into words is very, very helpful. Ordinary English. Functions whose value at 5 equals 0. So there are infinitely many functions. There are infinitely many functions that have this property. In fact, super infinitely many. But we can still analyze whether the set is closed under addition. Well, think of two functions that equal 5, very important, that equal 0 at 5. You can visualize them if you want. Their graphs, they would cross the x-axis at x equals 5. If that helps, sure. If not, don't bother. Functions that equal 0 at x equals 5. You take two functions like that and add them together. We have one function, f1 of x, that has this property. Put in another function that has this property, f2 of x. And of course, add them together. And the question is, does the sum have the same property? That its value at 5 equals 0. Well, let's plug it in. We plug in x equals 5. The first one is 0. The second one is 0. Their sum is 0. So yes, this property is closed under addition. What about multiplication by a number? I take a number c, or alpha is better, and multiply f1 by it. Does this new function still have the property that its value at 5 equals 0? You kind of have to repeat the words to yourself. And the answer is, I think so. Plug in x equals 5, we get alpha times 0, that's still 0. So this new function, which is a multiple of the original one, still has that property. So these functions do form a linear space because the set is closed under addition and multiplication by numbers. So yes, this is a linear space. Great. That's all this is. And it's the sort of thing that mathematicians do subconsciously. They just look at whatever it is they're looking at. In the future, it will be a differential equation or a property like this or something else. And they just ask themselves, if I take two of these and add them together, do I get another one of these? And if the answer is yes, that changes everything. And if the answer is no, boy, does that change everything. You'll see examples of it over and over and over again. Moving on to B. B. Well, the numbers are the same, they're just slightly different. Now, f of 0 equals 5. Not f of 5 equals 0, but f of 0 equals 5. Does that change anything? Similarly simple, just a short little description of what functions are in. Similarly, infinitely many functions belong to the set. Well, what about these guys? If I take two of these, f1 of x and f2 of x, and add them together, the only question I'm asking in my mind is, does this sum still have the same property, that its value at 0 equals 5? Well, let's check. We're going to plug in x equals 0 because that's the property we're testing. We'll get 5 for the first one, 5 for the second term in the sum, and so the sum will be 10. So this new function, I'll call it f of x, has the property that its value at 0 is 10. So does it satisfy this stated property? No, it does not. Does it belong to that set of functions? It does not. Is this set closed under addition? No, it is not. Does it represent a linear subspace? It does not. So it's not the numbers. It's not how simple the expression is. You really have to use your human abilities of analysis to answer the question. And you basically have to condition yourself, and you will soon do it subconsciously, of whether or not it's linear. Right now it seems like an idle question to you, but you will soon not be able to not ask that question. No, not a linear subspace. Okay, C. Oh, well, that's interesting. You might be panicking when you see this because you took calculus recently and you did not enjoy it. And this might make you feel like, oh no, this course will have calculus in it. How unpleasant. But no, not unpleasant at all. Just let's see if we can answer the same question. Let's take one function, f1 of x, that has the property that its derivative at 3 equals 0. I won't write it, we'll just remember it. Plus another function that has the same property, that its derivative at 3 equals 0. Does the sum have the same property? Okay, let's evaluate the derivative of this sum at 3. Well, you know how the derivative of the sum works. You apply the derivative to each term and then add them together. It's called the sum rule. A rule that doesn't deserve to be named anything. It's like naming a wall. Of course your room has a wall. Doesn't deserve a name. But anyway, it has a name. It's called the sum rule. Let's apply the derivative and evaluate it at 3. The derivative of f1 evaluated at 3, well, that's 0. Plus the derivative of f2 evaluated at 3, and that's 0. 0 plus 0 is 0. So yes, this sum has the property that its derivative at 3 equals 0. So this property survives addition. Does it survive multiplication by a number? Of course it does, and I'll just let you say the right words on your own here. Of course it does. So yes, this is a linear subspace. And it has very little to do with calculus. Only the sum rule, which is so intuitive, we shouldn't really call attention to it. If the sum rule didn't work, I don't know what calculus would look like. Moving on to D. Well, I'll let you answer this question on your own. But do you see how the 3 and the 0 traded their places just like they did before? And so once again, if you chose two functions that have this property and added them together, the derivative of the sum at 0 would be 6 and not 3. 6 is not 3. So the sum would not have this property and is therefore does not survive addition. Nor does it survive multiplication by numbers. If I multiplied my one function that does have this property by 10, evaluated its derivative at 0, the result would be 30, not 3. So it would no longer be in the set. So the set is not closed under multiplication by numbers. 10 times a function from this set is not another function from this set. So no, not a linear subspace. This property is not linear. And we can now move on to E. And I'll start accelerating a little bit. Oh, that's interesting. You just have to force yourself to imagine functions whose values are the same at 2 and 5. You don't know what that value is, but that's okay. Now imagine another function that has the same values at 2 and 5. And you add them together. Does the sum of those two functions have the same values at 2 and 5? If you just talk to yourself and describe to yourself in words what it is that you're trying to answer, if you ask yourself in proper English the right question, the answer will occur to you. So this is really the skill of asking the right question in proper English or improper English or in the language of your choice, or maybe without words if you prefer, but just ask the right question. And if you answer that question, then you'll have the answer to this other question. You know, and the question you're asking yourself is quite literal. It's not abstract, like, is it a linear subspace? That's a bit abstract. But does the sum still have the property that its value at 2 equals its value at 5 is a very matter-of-fact question. Moving on to F. Okay, does this A change anything? I'll let you figure it out on your own. It does not. G. Okay, not the value of the function at 3 equals the value of the function at 5, but the value of its derivative at 3 equals its value at 15. And here we're beginning to see mounting algebraic complexity without any increase in logical complexity. Because derivatives satisfy the sum rule, it does not complicate the logic in any way. You look at this and you might be intimidated. You start taking it apart from the linear algebra point of view, there's nothing to it. Nothing to it. Does not change anything. Just seeming algebraic complexity and no increase in logical complexity whatsoever. H. Well, here we see an innocent change compared to, I think it was part F. Not only are the values equal at 2 and 5, but they also equal 3. And hopefully now you're beginning to develop the intuition that having a constant like 3 sitting out there messes things up. Because when you multiply a function by 10, 3 becomes 30. But to preserve the property, it needs to remain 3. And so that 3 messes things up. Or if you take two functions that satisfy this property and you add them together, the resulting function would have equal values, and then it will equal 6 because it would be 3 plus 3, and 6 is not 3. So the sum does not have the property that its values at 2 and 5 equal 3. It has the property that its values at 2 and 5 equal 6. It's a nice property. It's just not the one that it should have. So no. No. I. Look at this complexity. Crazy. 3 evaluated at 3 different places, and it's the function, its derivative, and its second derivative. My goodness, second derivative. How much calculus is this? Not a lot. No different you start working through the appropriate logic and you realize it's linear. Okay, I'll let you work through the details. But another thing that I would like for you to start picking up on is that this judgment of whether or not something is linear is almost instant. Look at this, fourth derivative. Fourth derivative. Does this change anything? It does not. Moving on to K. Square. Interesting. So you will learn that the square messes up everything. So f squared of 5 does not mean f applied to f of 5. It does not mean that. Let's imagine a function that has this property. Can I think of a function like this? You know, I could probably even think of a linear function that has that property. Or how about this? F of x equals 1 has this property. There you go. What is its value at 3? 1. What is its value at 5? Also 1. Does 1 equal 1 squared? Yes, it does. So there you go. F of x equals 1 satisfies this property. Now let's consider a multiple of this function. Let's consider 10 of f of x, which equals 10. Does this new function, a multiple of the original one, still have the property that you see on the screen? You always test the result against the property you started out with. Okay, what is f of 3? 10. What is f of 5? Also 10. What is f of 5 squared? 100. Does 10 equal 100? It does not. This property does not survive multiplication by 10. It only survives multiplication by 0 and by 1, and not by 10. So this is not a linear property. And for this reason, you can always run this little test with a multiple. As soon as you see a square in the wrong place, and this is definitely the wrong place, you know that it's a non-linear property and that the space is not a linear space, that the set is not a linear space. Another intuitive point that I would like to make here, that you should develop a sense of whether what you're doing to f is linear. And here's what you can do to f that's linear. You can take f itself, that's linear. You can take 10f, that's linear. You can take the derivative of f, that's a linear thing to do to a function. You can take any order derivative, that's a linear thing to do to a function. You square a function, that's a nonlinear thing to do. Or more innocently, you add 1 to a function. That's a nonlinear thing to do. So when you're evaluating these, you should just, look for what's happening to f. And you'll develop an intuition for whether or not what's happening to f is linear or not. You can't answer that instantly. You have to run the two tests in your head. Closure under addition and multiplication by a number. So this plus 1, much more innocent than many other things we've seen, but that messes up everything. And you know how easy, what's an easy way to know that plus 1 messes things up? If you're closed under multiplication by numbers, then you should be able to multiply by 0, and the result should still be in the set. So in other words, the 0 function must be in the set to have any hope of a linear subspace. If the set you're looking at does not have the 0 function, you have no chance. And the 0 function does not have this property. So you know right away this is not closed under multiplication by a number, because it's not closed under multiplication by 0, because the 0 function does not belong to the set. So no. Well done, Pavel from Spring. Even functions. I don't want to get into the technical definition of even functions, and that it's the fact that a function is even if its value at x equals its value at minus x. You can see that this is hyperlinked. You can remind yourself of what an even function is. Think this through, and you'll discover that this is a linear subspace. And the next one, I'm guessing, is odd functions. Same thing. Okay. Final thoughts. These problems are simple. They're just an invitation to ask the pivotal question of linear space, which is the set closed under addition, and is the set closed under multiplication by a number? These problems are simple because they're immediately actionable. You know exactly what to try. You know exactly what matter-of-fact question to ask yourself and attempt to answer.